Hello everyone, my name is Li Chen. I'm currently doing doctoral research at Huazhong University of Science and Technology in China. The paper I will be presenting today is titled Personalized Federated Domain-Incremental Learning based on Adaptive Knowledge Matching. In detail, my presentation includes the following 5 sections. First, I will specify the background of federated learning and continual learning. Federated learning is a collaborative machine learning framework where a global model is trained by aggregating updates from multiple clients with local data. This approach allows for the preservation of data privacy, as the data remains on distributed devices. A prominent example of federated learning is the Fed-average algorithm, where the global model is obtained by averaging the parameters of local models from different clients. Incremental learning, also known as continual learning or lifelong learning, enables models to learn from a continuous string of data while retaining previously acquired knowledge. This approach is crucial for adapting to new tasks without forgetting what has been learned before. There are 3 primary scenarios in continual learning. In class incremental learning, different tasks introduce new classes, and in domain incremental learning, different tasks introduce new domains or distributions. While in task incremental learning, both the classes and domains change across different tasks. Despite the advantages of federated learning and continual learning, several limitations exist. On one hand, a significant challenge is the difficulty in retaining previously learned information while learning new data, which is also known as catastrophic forgetting. This issue is exacerbated when the data is identically and independently distributed across devices. On the other hand, current federated incremental learning methods just focus on the class incremental tasks. The label information is employed to transfer knowledge between different tasks. However, these methods will fail to work with domain shifts between incremental tasks when the classes remain consistent. As shown in the left figure below, most existing works focus on either temporal heterogeneity or spatial heterogeneity, respectively, and just a few research address the combination of 2 issues together by federated domain incremental learning. In our research, we aim to address the following 2 main questions: how to discern the similar knowledge between domain incremental tasks, and how to transfer the shared knowledge. To tackle these problems, we propose a PFET-DLL method to adaptively match and migrate the knowledge among different incremental tasks. This method includes the following key steps. The first step is the knowledge matching. To access the similarity between different incremental tasks, where a higher similarity indicates a greater amount of common knowledge, we propose a knowledge matching intensity. When it comes to the new incremental task, each client first needs to compute the knowledge matching intensity between the new task and the previous tasks. We define the auxiliary classifier theta for the corresponding local task, which is trained by the discrimination of the sample belonging to the task. The auxiliary classifier can output the similarity between different tasks based on the extracted feature representation. Next is the strategy selection. After acquiring the knowledge matching intensity role in step 1, the client can select the appropriate incremental task learning strategy. An intuition is that the client will prefer to train with previous personalized local models when the knowledge matching intensity exceeds the lambda, which means a high-level similarity between the new task and the previous tasks, so that the model can converge on the new task with slight adjustments. Besides, the client will sacrifice some storage by training the new task with the new initial model parameters to ensure accuracy for both the new task and the previous tasks. The last step is the knowledge migration. Then each client migrates the knowledge from other existing personalized local models to assist the training with a calculated knowledge matching intensity. In our experiments, 3 common datasets and both representative FL methods and FIL methods have been used to verify the effectiveness of the proposed method. We assess the performance of the PFET-DLL in terms of test accuracy and ablation study. Our results demonstrate that PFAD-DIL significantly outperforms the state-of-the-art methods, achieving up to 14.35% improvement in final accuracy. Furthermore, through ablation study, we proved that all modules in PFAD-DIL effectively contribute to the model training. Then, we conduct experiments to evaluate the parameter sensitivity and communication efficiency. As shown in this figure, all methods achieve an improvement in test accuracy with a decline in data heterogeneity, and PFAD-DIL consistently achieves a leading improvement in performance with different levels of data heterogeneity. Then, we conduct more research on the setting of hyperparameter lambda. From the left table below, PFAD-DIL consistently outperforms other baselines, even when lambda is simply set to 0.5 across all datasets, around 2 auxiliary classifiers per client in Digit10 or Office 31, and approximately 3 in Domain-Net. The flexibility of PFAD-DIL allows users to tune this parameter based on their specific requirements and constraints in real-world scenarios. Finally, the training time of each round and the sum of communication rounds required to achieve the performance on each task is shown in the right table below. Vividly, the training of the auxiliary classifier will not increase the overhead or computational complexity significantly and hardly affect the training efficiency. PFAD-DIL requires the least communication rounds to achieve the reported test accuracy on all datasets with the knowledge matching. In conclusion, we seek to tackle the catastrophic forgetting in the FDIL scenario. We propose a personalized federated domain-incremental learning approach based on adaptive knowledge matching named PFAD-DIL. We leverage an auxiliary classifier to calculate the knowledge matching intensity for the incremental task learning, strategy selection, and knowledge migration. Furthermore, we propose sharing partial parameters between the target model and the auxiliary classifier to condense model parameters. Our extensive experiments across various settings and baselines validate the effectiveness of PFAD-DIL, making it a robust solution for federated domain incremental learning. Thank you for your attention. If you have any questions or need further information, please feel free to reach out to us.